a little reminder. If you did long division or synthetic division, you could write a division statement. And that division statement was that your polynomial is what you divided by, times by your answer, and then if there was a remainder, you had to add it. Now we could take this same division statement and rearrange it by dividing everything by d. And this is going to be what's going to be helpful for us with our integrals. That if you have some polynomial divided by d, you could rewrite it as the quotient plus the remainder would still need to be divided by d. So just a little bit of simple math to show how this even works with simple math. If you were doing long division with, I want to divide 24 by 7. I'll put this at the bottom. If you wanted to divide 24 by 7, long division would say, well, there's 3 of them, which would give me 21, which is as close as I can get to 24 as possible. And then if I subtract, I would get a remainder of 3. Now, the first division statement says P equals dq plus r. In real numbers, this means that 24 equals, I was dividing by 7, I got 3 as a quotient. That got me close to 21. I would still have a remainder of 3. That is that statement with regular numbers. This statement with regular numbers says that if I took 21 and I divided it, 24, and I divided it by 7, I should get 3 plus, I would have a remainder of 3 that still needs to be divided by 7. So I would get 3 and 3/7. I could write it as a mixed fraction. That's what it means for numbers. Okay? So what we're going to do is we're going to look at questions which have a division and then say, if I actually divided this and I wrote my division statement, that means I could rewrite this because here I have some polynomial divided by something. I could see what answer I get, plus my remainder would still need to be divided by whatever I'm dividing by, which in this case is x minus 2. If that remainder is just a nice number, maybe you can see already that if you had a 3 over x minus 2, that works out nicely with the natural logarithm. Because the integral of 1 over x is the natural log of x. So what does this look like for us? First of all, we could use long division or synthetic division and divide. Remember, we use the coefficients 3, -1, -5, and 1. If you're dividing by x minus 2, you put a positive 2 out in front. Bring the first number down, multiply, then add. 2 times 5 is 10, then add. 2 times 5 is 10 again, and then add. And you would get that P divided by D is equal to this quotient, and then we still have a remainder of 11 that still we would need to be divided by D. So I just called this whole top part here, this whole thing f of x. That's my polynomial divided by D. I did my synthetic division, my long division. I got it into a new form, and that new form is easy to do the integral of. Because 3x squared, integral would just be add 1 to the exponent divide, x cubed. Add 1 to the exponent divide, 5x squared over 2. 5 will just become 5x, and then the x minus 2 will become 11 absolute value of x minus 2 plus c. And in these long division ones, what's always going to happen nicely is you're going to get a remainder over an x plus x minus something, which will always be a natural log. And that will compensate for that divide. So try the next one. Set up your long division. Okay, long division looks like this. You put a 3x minus 5 out in front, right? What would multiply 3x to get 6x to the 4? A 2x cubed. Then you multiply 2x cubed by the 3x minus 5, giving you 6x4 minus 10x cubed, and you subtract. So I've done this color-coded in steps, because it just repeats the steps for every color. Every time you look at your first term and say, what would multiply to give me that first term? So after completing the blue step, now my first term is a 3x cubed. What would I have to multiply 3x by to get 3x cubed? I need to multiply by 1x squared in green. Multiply that x squared by 3x and by minus 5, put it in brackets, and subtract. And we repeat this process until we get to the very end, where we have a remainder of 20. Which allows us to rewrite our integral as the quotient plus the remainder divided by 3x minus 5. No recollection of long division? Okay. This one has a whole bunch of stuff connected in all of our advanced techniques. Okay? Okay, starting here. We do our long division. It works out nicely to just be x, and then this is your remainder. You would have a remainder of 6x plus 12. Because as soon as the power is less than what you're dividing by, it's a remainder. So we rewrite our integral. This just becomes x plus 6x plus 12 divided by x squared plus 1. So unfortunately, this looks nice to do the integral of, just the x. It's like, okay, I can handle that. That'll be x squared over 2. But this part, the 6x plus 12 over x squared plus 1, needs to trigger a couple of things. It needs to trigger substitution, because if I make the u on the bottom x squared plus 1, the derivative would be 2x. But unfortunately, what's on the top is not just an x, it's 6x plus 12. The other thing that the x squared plus 1 should trigger for you on the bottom is the integral of tan inverse. So we're going to unadd the fractions at the top. If I unadd those fractions, the first part fits nice with substitution. The second part fits nice with tan inverse. So when you saw the answer and saw tan inverse, and we're like, where'd that come from? Now we can see that. So we do each integral separately. Beautiful. Integral of x, that first one is just x squared over 2. The second one, the integral of 6x over x squared plus 1, is a nice substitution one. If you let u equal to x squared plus 1, then du would be 2x. We need to get a 6x, so we can multiply both sides by 3. and do our substitution, which nicely becomes 3 natural log of u, which u was x squared plus 1. And if I do the third integral, which is 12 over x squared plus 1, that's just 12 tan inverse. So when I did each of those integrals separately, they all would be plus c, but they would be plus different c's, so I used like c1, c2, c3. In the end, your final integral will just be plus c. Some people are able to just do that. It wouldn't be bad if you went from here to here. If you could do that, that's not too bad. But I think it does make sense to do each one separately. Show your work that way. All right, check how you did on this one. So you have to use long division. You get x minus 4, and then your remainder is 18. Which means we can write this as x minus 4 plus the integral of 18 of x squared minus 2x plus 2. And this x squared minus 2x plus 2, and this part is easy. But the x squared plus 2x plus 2, we're going to have to use that completing the square technique. And then you can make ux minus 1. So this will be a tan inverse. Oh, I forgot. See an 18 here. X and 18.